So can't wait for that. That'll make next week very exciting. But first we have some groundwork to lay here in terms of 2.2. So everybody on page 3 of your notes now? Does that sound about right? And we are going to talk about direct variation and inverse variation. So I want you to think about two situations. All right, I'm going to give you an example of each. All right, I pull into the gas station. I'm going to buy some gas. Obviously, I'm going to buy some gallons of gas and I'm going to pay some money, right? The more gallons I buy, the more money I pay. Would you agree with that? That's called direct variation. When both of your variables are growing, or I should say moving in the same direction, both getting bigger, more gallons, more money, that is direct variation. And the formula for direct variation is y equals kx. There's probably a reason people use the letter k, but really think of it as y equals mx, because k is functioning just like the slope does in an equation. A direct variation line looks like this, right through the origin. That's a direct variation equation. Two things vary directly if they are moving in the same direction. Okay? Now the opposite of that, think about this for a second. I get in my car that now has gas, and I'm going to drive to school. The faster I drive, the less time it takes me to get here. Would you agree? Speed and time are inversely proportional in that case, because as my speed increases, my time is decreasing. Do you see the difference? That's called inverse variation. And the equation for inverse variation is y equals k over x. Y equals k over x. So I've given you the general equation, I've given you an example. Power functions, very simply, are any equation of the form y equals ax to a power. And that power can be anything except 0. So examples of power functions would be y equals 2x squared, y equals x to the 1/5, y equals x to the -8. Anything to a power, x to a power, is called a power function. You know, the next chapter, we'll talk about exponential functions, and that's when x is the exponent. But when x is the base, when x is right here, that's called a power function. Now, I've asked you a question. Think about all of your BFFs, all of them. Which ones fit this mold? Squaring, absolutely. The squaring is a power function. Cubing, absolutely. Linear, you got it, because that's x to the first, right? And that exponent can be anything except 0. There are some more, and these are a little bit sneakier, but this is actually a power function, because square root is really what power? Do you remember from last year? 1/2. So this is really x to the 1/2. So that is a power function. So is this one. Because 1/, is really just a negative exponent. How many have we got? 1, 2, 3, 4, 5. Sine and cosine aren't. Logistic is an exponential logarithm. What am I missing? I'm missing two. Oh, greatest integer is not. Which one? I didn't say one of them. Huh? I can't hear you. This is the reciprocal. I counted these 5. I'm trying to think. I've only come up with 11. I want to make sure the one I'm forgetting is not 1. Oh shoot! Which one are we forgetting?
Absolute value.
Oh yeah, there it is. Absolute value. And it is not a power function. So we've got them all. All 5 of these right here. These are the power functions of your BFS. It's almost half. Almost half. All right, now I want you to look in your book on page 197 because there's a little graph there. There's nothing special about these exercises, but I want you to start thinking about how the shape of the curve tells you a lot about your equation. So if you look at let's look at just the first quadrant in that picture. We got a shape that looks like this. They call that A. Then we've got a shape that looks like this. They call that B. We've got one that looks like this. They call that C. Oh no, they call that D. And then C is just 1. Okay. Now your job for all those exercises, I did turn this on, didn't I? Oh. Your job for 37 through 42 is just to identify which of those curves, and they've got the same thing down here in quadrant 4, which of those curves matches these equations. So look at number 37. It is x to the 4th. Now that's not one of your BFFs, but x to the 4th is going to behave like x to the 2nd and x to the 3rd behave. So which of these looks like your x to the 2nd or x to the 3rd? Which of these, A, B, C, or D? Looks like a piece of x squared or a piece of x cubed. D, definitely D, right? Isn't that what both curves do? Don't they both shoot up like that? That's what x to the 4th is going to look like. The problem is they put a negative in front of it. So instead of looking like that, isn't it going to look like this? So x to the 4th goes with G, or 37 goes with curve G. All right, what about 38? 38 has a negative exponent. Which one of your BFFs has a negative exponent? This one, right? Which of those curves matches this? A? Isn't that A, the reciprocal function? So that's going to be number 38. The negative exponent ones are going to resemble the BFF that has a negative exponent. All right, now what about 39? 39 is a fractional exponent. Which of these has a fractional exponent? Your square root? Which of those curves looks like the square root? D? That's the answer to number 39, D. How about number 40? Now this one is tricky. This one's tricky because when you see that fraction, you immediately think, oh, that's going to look like the square root, because I didn't explain it very well. If the power is less than 1, it's going to have the square root shape. If the power is greater than 1, it's going to have the square and cubing shape. So even though problem 40, there's also a negative on there, I gotta take care of that too. But even though problem 40 has a fractional exponent, the fraction is greater than 1. So that acts like a squared. So the answer to 40 is actually G, because there's a negative in front of it. It would be B in quadrant 1, but it's got a negative, so it's G. 41. What do you think about 41? It has a negative in front of it, and it has a negative exponent. Which one's that going to go with? Okay, negative exponent. Which shape is negative exponent? That would be A, right? But there's a negative coefficient on it, which pops it down here. So which curve is that? That's H. Now D, be careful. Look at that exponent. Less than 1, right? So it's less than 1, so it's going to look just like this one. So, tell me general shapes. If you're A, these are all power functions. If you're A, your exponent is negative. If you're B, your exponent is bigger than 1. If you're C, your exponent is 1, your line, x to the first. And if you're D, your exponent is somewhere between 0 and 1. It's a fraction, like 1/2, 2/3, 3/5. Does that make sense to everybody? Power function pictures. All right, look at, on this same page, 17 and those, let's look at a few of those. The area of an equilateral triangle varies directly, there's your format for varies directly, as the square of the length of its sides. So what would that equation look like? Anybody have an idea? This says y varies directly as x. That's how I would say this out loud in words. Y varies directly as x. So what would be my equation if area varies directly as the square of the side? Right there it is. Engage, engage, engage. I know you're bored, you want to get out of here, but oh my gosh, think about it. The volume is proportional to the square of its radius. The word is proportional to is just another way of saying varies directly. So if, when you say is proportional, that means varies directly. Sometimes it says inversely proportional, and that would mean inverse variation. But this just says varies, or is proportional to, that means varies directly. So volume is proportional to the square of its radius. Kids, it's that easy. Number 20, Charles' law says that the volume varies directly, oh wait, no, I'm doing that, oh, I skipped, this is 20. Volume varies directly as the absolute temperature T. That's 20. Now we'll do 19. The current is inversely proportional. See how I'm setting it up now? Because it's inversely proportional to resistance R. All right, you do 21 and 22. See if you can do those. And what's a little different is they don't use K. Don't let that confuse you. So if I were doing 21 and it says energy is proportional to mass M, I would say this. This is called my constant of variation. In this problem, they say don't use K, use C squared. Okay, so it looks like that. The format is still this. They're just telling you to use a different constant. So did you get 22? The speed P of a free-falling object varies as the square root of the distance d with a constant of variation k. So varies, if they don't say inversely, it's directly. So that would just be kd. But instead of using k, what do they want me to use? The square root of 2g. Easy, easy, easy. All right, I'm gonna skip number 3. And go straight to, shoot, I'm out of time. So maybe I won't skip 3, maybe we'll hit that another day. But we're out of time now, so we'll have to finish that next time.